Hi, I'm Holo.
Hi, I'm Zaid Siddiqui.
Hi, my name is Han Sun.
Today we're going to present to you our research on Boeing 787 wing flaps.
Here's our introduction to our Boeing 787. The manufacturer is a Boeing commercial airplanes. There are seats of 242 to 335 passengers. They're using the engine of Rolls-Royce Trent 1000 or the General Electric GNX. The dimension of the length is 56.72 meters and the wingspan is 60.12 meters. The extended wing flaps increase the camber or curvature of the wing, rising the maximum lift coefficient, and it allows the aircraft to generate the required lift at lower speed. It also reduces the stalling speed of the aircraft and reduces the minimum speed at which the aircraft will safely maintain flight.
Next, we will look at the mechanism for the wing flaps in detail. The wing flaps each work individually of each other. This means that we can treat them separately. Therefore, we selected the portion of the wing flap opening down as the main topic of research. To begin, we treated the wing flap mechanism as a 4-bar linkage. Link 1 is the driving hand of the mechanism. All of the movement begins from this link. Link 4 acts as ground. This means that points B and C are stationary and have zero velocity. The wing flap is an extension of link 3 to the right, however, is shown only connected to point C for calculation simplifications. Link 1 pushes link 2, and as that happens, link 3, or in other terms, the wing flap, pushes down. Now we're going to look at the dimensions of the wing flap. So link 1 is 10.9 centimeters, and that's this link right here. Link 2 is 34.8 centimeters, so that's this one. Link 3 is 26.1 centimeters, that's this one. And link 4 finally is 47.8 centimeters, and it connects links 1 and 3.
The wing flaps located on the trailing edge of a fixed wings aircraft wings. To lower the minimum speed of the aircraft that can be safely flown. It also increased the angle of descent for landing. It increased the drag and it is also retractable.
So taking a look at the Grashof 4-bar linkage system, we can first see that link 1 is indeed the shortest, so we can label that as the S link of our system. And taking a look at link 4, this is, comparing to the rest, the largest and the longest, so we can label that as the L, which leaves us link 2 and link 3 becoming P and Q. Now, due to the Grashof's equation, the sum of S and L, if is less than the sum of P and Q, we are able to conclude that it is a type 1 system. And looking from the mechanism used in the plane wing flaps, we can conclude that it indeed does match up with the calculations, ending up with a type 1 crank rocker system. Next, we will look at a 3D model. So starting with the 4-bar linkage mechanism, inside the wing flap, we can clearly locate the 4 bars, one being here, 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 and lastly, connecting both of them in the back. Now these 4 bars will function first by rotating the motor arm. By rotating the motor arm, it will push the second linkage, which will then push the wing flaps down, allowing an exact 43 angle to be achieved of the wing flap. Now doing so will shape the wings into a new form that allows more drag, slowing down the plane, and achieving its purpose.
So as discussed earlier, both of these flaps work independent, and as Han just said, this one goes down and that one goes up, and you can see that the one that goes down is connected to this 4-bar mechanism. However, the one that goes up is completely independent and is not connected to this at all. Okay, so now we're going to look at the acceleration diagram. At the end, it's going to look something like this. So before we begin this, I'll give you some ground rules on how to do this. So let's say you have your link over here. If we were to do a velocity diagram of this point relative to this point, saying that this was fixed at ground, it would be perpendicular. And if this rotated this way, this would be your direction for your velocity, and if the other way would be your direction. Okay, so we just explained how the velocity diagram works. And it's shown here on the right-hand side. So point OV is equal to VB, VC, and also 0 centimeters per second. Remember that this is in centimeters per second, the scale. Up here shown 1 centimeter equals 3 centimeters per second. VA is 7.358 centimeters per second, and it's this line right here. VD is 6.525 centimeters per second, and it's this line. Remembering that the velocities are always perpendicular to the actual direction of the linkages themselves. VE, which is also the velocity of the wing flap, is this long one down here, and it is 39.375 centimeters per second. Now, if we do the acceleration for this link, it won't be perpendicular. It'll be parallel, and it'll face downward to this point. But all points that have 0 acceleration are represented by point OA. And the acceleration, instead of pointing to it, it'll point in the direction of that. However, it'll point away from point OA. Now we can begin and analyze our acceleration diagram. So we said that our link, our 4-bar linkage, looked like this, where that was point E, C, D, B, A. We gave this a constant angular velocity. That means on the acceleration diagram, this would only have a normal component and no tangential component. So that's right over here. AD, we didn't write N because this is the absolute velocity of D relative to ground. Next, we find the next point, which is connected to ground, and that's point A. However, this we don't know for a fact that it has or has not a constant angular velocity, so we have to draw a acceleration in the direction of link AB, starting at OA. Then we can draw a tangential acceleration component. And once we draw a tangential acceleration component from point D, we know that we have an intersection here, which means that this acceleration is indeed of point A, and we can label it as AA absolute. Now, let's look at something a little more complicated. The shared acceleration of link 2 between point A and D. We have to look at it from both ways. We calculated acceleration AD normal to be 2.05 centimeters per second squared. So we draw that, starting from A going to D. We also have a tangential component. And because it's shared by point D, we must also look at the tangential component of point D, which is this line here, and they intersect at that point. So really, the normal component and the tangential component, when you take the resultant, ADA is that line over there. And that's this number right.
Now let's take a look at the animation of the wing flap. So as we can see, the 4-bar linkage rotated, allowing the wing flap to turn from this position downwards in a 43 degrees angle. We also designed the top wing flap to be able to rotate by itself, and increasing the accuracy of our simulation.
From research, we found out that Boeing is using the carbon fiber as their exterior structure, so we can see that in this part and this part, they are using the carbon fiber. So for the linkage, we chose the titanium because it's corrosion resistant and it has a long fatigue life.
So now let's take a look at the disassembly of the mechanism along with the